So I'm going to be talking about optimizing compression performance in Q/KDB. So this is inspired by a couple of blog posts you may have seen me post on LinkedIn recently. And so this is supposed to, complement that material. And I kind of got into it just because in a lot of definitely a lot of places I've worked, and maybe a lot of developers out there have find this as well, that you go in and someone sets ZD to some default value. There's no reason why. Someone's just gone, oh, those numbers look good, let's just use those. So I kind of went on a discovery mission to find out, what's the best compression parameters to use in your KDB setup. So go back and show. So today we'll be looking at, or I'm going to start with a quick look at what compression is, just to set the scene. I'm going to give a quick example of a common compression algorithm called run-length encoding. So just to help visualize what's going on behind the scenes when compression is going on. Then we're going to jump into look at KDB's built-in compression features and what compression parameters you can actually provide to KDB. And because it can be quite overwhelming to actually choose those parameters, I've created a tool that I've been using to actually run a comprehensive test of different combinations of parameters, and hopefully you can use it or something similar to run your own tests on your own data. So what is data compression? Data compression is the process of reducing the size of a data object, such as a file or data set, to optimize the storage efficiency and improve performance in data transfer and retrieval. And this is achieved by restructuring or encoding information using fewer bits than the original representation. So there are two types. We have lossless, which is what we're concerned with in KDB land. And this is where we preserve the ability to reconstruct the data accurately. Obviously in finance and things like that, you don't want to be losing any information. But just to be aware, there's also lossy, which is where data is reconstructed approximately. So you get this in things like MP3, where frequencies outside the human range of hearing are actually removed. And you get it in JPEG, where the resolution of the image is actually reduced. So if you compare a JPEG and a PNG, you'll notice your JPEG images are usually lower resolution. So a quick example, just to help visualize what's actually going on behind the scenes when we're talking about compression. So run-length encoding is a common algorithm that identifies consecutive sequences of the same data value, and it stores them as a count value pair instead of repeating the value multiple times. This is particularly effective for sorted or repetitive data, where long runs of identical values occur frequently. So I've chose this example because later we'll see how sorting your data can actually give dramatic effects on your compression performance. So this will help you understand exactly why or what's going on that helps that. So quick example, I've got these numbers. You might notice the significance of the numbers I've chosen. But basically, it's this long run numbers. This isn't necessarily in contiguous or even sorted order, but you can see their numbers are grouped together. So we have like 3s, 1, 4. And if I was to apply the RLB algorithm to this, I would go from this 28 number list down to this 12 number list. So it's actually storing the number 5 3s, 3 1s, 5 4s, etc. You can see what the benefit is here of data where you have long runs. You might also see what the downside might be if we have very unique data. I mean, in the worst case, if we had a complete unique set of data, we'd actually end up doubling the memory. So KDB has its own features optimized for columnar storage and for time series analytics. And we're going to jump into that. So how would we do some common file operations normally in KDB for just uncompressed data? So here I just have a few simple code snippets. So we use the keyword set and file name on the left, data, so that's how we would save data. We have how to get data or load data, and then we also have upsert, which is how we can append data to a file. And at this point in another programming language, you might want to, or to do compression, you would have to reach for some library. You might have some if-elses. Q has this all built in natively. The only change is to actually add the compression parameters. So here, the 3 numbers there, and I'll get into more what they are. But that's the only change. Get and upsert didn't change at all. They have it built in. And I don't even need to provide the parameters directly to set. That's only if I need to do it explicitly for that file. I can give this set global defaults using .z.d, and that will actually now mean that anytime I use set, that compression is going to be applied to the data. So now let's have a look more into what the actual compression parameters are. So we have the logical block size, we have the compression algorithm, and we have the algorithm level. So the logical block size dictates the amount of data compressed in each block. The compression algorithm is the actual algorithm we're using to compress the data. So this is your QAPC, your gzip. We'll see which ones are supported in KDB coming up. And we also have the algorithm level, which is a tuning parameter used by some of the algorithms to determine how much compression to apply. So larger levels are generally mean more compression. So we're actually going to dive in now just deeper into each of those. So as I said there, logical block size dictates the amount of data compressed in each block. And this plays a significant role in both compression efficiency and performance during data access. So here I have a little example of the actual possible values for LBS. So they range from 12 up to 20. Each of these values represents the power of 2. So 12 to the power, 2 to the power of 12 is 4 kilobytes, 2 to the power of 13 is 8 kilobytes, etc. And generally, as you go to a larger LBS value, you get larger size reduction with the expense of read and write speed, and vice versa for going to lower values. So just to apply to our RLE example that we had earlier to see how using different sizes of blocks can affect the performance. So using a small logical block size, we have here, I've just taken the numbers I had before, the 28 numbers. You can see each block is actually compressed individually. So it's basically a separate environment. And you can see that the runs, for example, in the first two blocks, the threes is actually interrupted, which means that you can't compress as efficiently because I chose too small of a logical block size. However, if I use a larger logical block size, you can see that, again, looking at the first one, that run of threes was not interrupted, and we actually got better compression. So in the smaller one, we went from 28 down to 22 numbers, and second case, we went down to 16 numbers. However, sometimes selecting a larger logical block size might not give you any benefit. It might cost more write to read speed. So it is about balancing those parameters, and that's kind of what the tool I've developed is going to help do. So we'll see that a bit. So just to cover the compression algorithms and level as well, as of Q4.1, there is 5 supported algorithms. So you can see them there. You provide them using this number, 0 is for no compression, and then 1 to 5 are the unique IDs. So we don't specify them by name. And you can see there, not every algorithm has a concept of level, but you can see there the actual range of levels. For example, gzip goes 0 to 9. QAPC is the compression algorithm built into Q, so you get it out of the box. The other algorithms, you do need the library files on your system, or KDB will throw you an error, but usually installing was quite easy using package managers. Here's just a quick example of how we can, just to see how we can provide different values. So you can see here I've just used a fixed logical block size of 16. And then the first one is 1, so that corresponds to QAPC at level 0. Then the next one is 2, gzip at level 6, and then 5 is the ZSTD. But that's just to show a quick example of how they can be used. So now that's kind of the overview of compression in KDB. Now jumping into the actual doing a performance test. So we look at certain measures when we're doing a test. Those measures are the compression factor or ratio. So that's the ratio of uncompressed size to compressed size. And this measures our space savings. Higher values indicate we're actually compressing more, we're saving more space. We look at write time, which measures how quickly data is compressed and written to disk. So this is the actual algorithm running, and then the actual physical write to disk. And we also want to do this as quick as we can, so lower values are preferable. Similarly for read time, we want lower values, and this measures how quickly we can compress we can actually read the compressed data from disk and decompress it. So the tool, just to give a quick intro to that, this is the tool that I wrote specifically when I was doing the blogs. So it's pretty easy to use. It's on my personal GitHub. You can just go download it. So it provides functions to measure compression performance. It allows you to test combinations of compression parameters. The results are actually averaged over multiple runs. They were just the noise that you get from uncontrollable system-related factors. So because we're doing writes and reads, we're obviously using a lot of disk time, and there might be other processes running that are trying to do that as well. So by doing an average over a few runs, you get a more accurate result. And you can run this on your own data set, or the tool also has functions to generate your own or random data sets, which helps you cover the general case, just in case you don't know what your data is going to look like. So now I'm just going to go on to an example. So here I've just got a simple splay table. It's not actually lining up there 100%, but you can see the column names there. So just the standard splay table for trade data. We see a lot of these examples throughout code.kx. They've got 10,000 records here. So there's various functions available that I've provided in the tool, but the most comprehensive is this test all function. So this does every combination of LBS algorithm on level. And you can see the output is just basically each row corresponds to a combination of LBS algorithm level. And then it gives you some metadata about the actual data itself. And then you can see the results of like write time, read time, and compression factor. And then test time is just how long your test, because each test has run multiple runs, so it might actually be longer. But that's just, an indication of how long the actual test took itself. And then specifically for doing a splay table test, so here I've got a test slide function. It takes as the first argument one of those functions. So here I've given it the test all. The second argument is the path to the root of your database. The third argument is the path of the table under the root. So here I just have trade because I'm doing a splay table. But if you were doing a partition table, you could also give this, the date/trade. And the last argument is the column names, or you can give it the null symbol, and that means do it for all my columns. And it produces a dictionary mapping each column to its corresponding results table. So they're just indexed into the size column to see its results table, which is what I had in the previous slide. So then, obviously, what do we do with this results table? Something like this to generate a summary table. So, for example, generating the maximum values, the minimum, and the average. So the maximum, you obviously want to maximize your compression factor, and you want to minimize your write and read time, but also the average, because maybe you want to just, be at least as good as the average case. But this just gives you an overall summary of your results. But you can also then dig in a little deeper. Say you're only interested in getting the max compression factor, you can do a query to see, which combinations of my parameters produce those values. Similar for read and write time, but you can also tweak these to say you wanted to beat the average case. So you can, alter your where statement to say, where compression factor is greater than the average compression factor. And then you also want to get a certain write time, so you can customize those queries. There's just some examples of queries that can be done. So I had a graph like this on my blog posts, and I thought they're quite cool for zooming into a certain algorithm. So say which algorithm you want to use, like the ZSTD here is like the newest one provided for KDB. This shows what happens for the ZSTD for a fixed LBS of 17 as the level increases. So generally, as we increase the algorithm level, that's supposed to be being a more aggressive compression, and you'd expect the compression factor to rise. You can see here it actually rises at the start, but then drops off again. So just choosing, the most aggressive values might not necessarily give you the best results for your data. So that's why a test like this needs to be run. And here, although the read time looks very negligible compared to the other ones, remember that your data is going to be read a lot more than it's written usually. So you might want to zoom in on something like that and see, what level will give me the best read time. And the write time here does do exactly as you would expect as you compress more. You have to work a bit harder to do that compression. So here from this graph, you can see that the best level to choose would be like 0 or 3, 4, 5. So it's not necessarily just choosing the most aggressive value. So just kind of to finish off here, we have the effects of data type on the compression performance. So here I have, this is the summary table I had a couple of slides ago for the long data type, which is the size column of our trade table. And you can see there the average compression factor was about 5. And then I did the same test for the price column, which is a float data type, and you can see that the average was about 1.26. So higher values are better usually for meaning more compression. So it just shows you how data type can actually affect your compression. You will notice here the very last times on the average, I know it's not lining up here 100%, but just the very last column of times, the write time, the average write time for the long type is actually greater than that for the float. That is because we're able to compress more, and we're going to spend more time doing that compression, whereas the float's going to just bail out early because it can't be as compressed as well. So that is something to keep in mind if you're more interested in the write time. And because data type is something that maybe you might not have full control over, you might have some control, especially in the case of choosing to do a float or a long. If your floats are you're never going to use the decimal point, for example. And then the effects of sorting. So this is the most extravagant results. You can see there that the improvements to the average for sorting for the compression factor was 2,155%. That is just from a simple sort, and it just shows the benefits that can be achieved through sorting. And again, you can only really sort on one column. Well, you can sort in multiple, but usually it's the first column that's going to be the driving one. So making that decision of which one to sort, which column am I querying the most, is definitely very important. And these tests like this can show you that. But that's everything I had to cover. Here I've got the links to the Q tools, which is where that tool is, and my own personal links as well, if you want to get in contact if I can't answer any of the questions here. But yeah, thanks everyone for listening.